This module, we're going to take a look at some of the network services that are available within Azure networking. Now, two particular services we're going to look at, Azure DNS and also the Azure Network Load Balancer. So Azure DNS is essentially a DNS server service that is native to Azure. So instead of you having to build your own DNS server, configure port rules, etc., you can simply use an Azure managed DNS solution and manage your rules, DNS configuration via the Azure portal without having to worry about the underlying Azure DNS server itself. Now, why is this important? Well, if you have an investment in Azure for web applications, you want to ensure that DNS name resolution is incredibly fast. So take a look at some of the data right here. On any given website that a user requests, on average, that website generates anywhere from 16 to 18 DNS queries to load that single website. That's kind of an industry average. Now, if you have a poor DNS implementation, let's look at the two charts here in the bottom. This one on the left is an example of a good DNS implementation where the user spends most of their time waiting for data to come back as opposed to for DNS name resolution. The one here on the right is a poor DNS implementation where the amount of time the user is spending is heavily loaded down on DNS. This is a bad situation. Anytime DNS is the reason a page loads slowly, that can result in people not going to your site, not spending money, whatever the case might be. Bottom line, rapid, effective DNS resolution for all the components of a web application is critical to the performance of the web application. If the web application is running on Azure, then it makes sense to also have the required DNS that's managing that web application native on Azure as well, so you get that better performance because the DNS is closer to the application. So by default, this supplies name resolution for virtual machines and networks, but you can also create custom zones within DNS to be able to create your own managed DNS implementation, where you can create whatever DNS records you want, just like you can if it was a DNS server you installed in your local network. You can then delegate control of your zone using whatever DNS registrar you're using. For example, if you're using Network Solutions, you can go to Network Solutions, indicate that the Azure-based DNS servers are the ones that are managing your zone, and then manage all your zone records directly within Azure itself. So there's a couple of concepts to understand when we think about Azure DNS. We have DNS zones. A DNS zone is a container for a record set. So, for example, sales.contoso.com, that's a DNS zone. Production.contoso.com is a DNS zone. A record set is a collection of records with the same name and type. The common industry term for what happens with a record set is DNS round robin. And so this has been a popular way that, that folks have used to have, if I have multiple copies of a web application and I want to balance the traffic between them, one of the cheapest and simplest tricks has always been DNS round robin. I simply create two entries for the app with two separate IPs, and the DNS server will hand them out one at a time and alternate, or 3 or 4 or however many. That's a record set. A record is an individual record within that set. So this example right here, contoso.com is the zone, the record set is www, and the individual records are the 2 IP addresses that are listed. Zone delegation is when you delegate authority for a particular zone to Azure. And with any zone you create, Azure is going to list the name servers that manage that zone for you. So you then go to your registrar, whoever the base registrar is of that particular zone, and you can list the Azure name servers as authoritative for that zone. Any queries will then be sent to those Azure name servers, and any DNS work is going to be resolved directly on Azure. And so you can do this with PowerShell. You can do this with any of the available Azure tools. Speaking of PowerShell, you can manage Azure DNS with PowerShell. So here's some simple examples. Select the subscription, create a resource group, create a new DNS zone, which is adatum.com, and then retrieve the start of authority and name server records for that zone, and then create a new www resource record with a particular IP address on it. In addition, with Azure DNS, there is an integration component that's available. Azure supports what are called e-tags so that you can programmatically manipulate and update Azure DNS. Now, e-tags are a mechanism that help manage concurrency through web applications. An e-tag is like a version number on an application. Now, if you're programmatically changing DNS to something that's familiar to you, the whole point of this is you can manage Azure through things like REST and .NET and Java. Problem being that, or I shouldn't say problem, but solution being you can use e-tags to manage concurrency when you do this. So that's our look at Azure DNS. In some of the demos we'll be showing you a little later in the course, you'll see us set up a zone, delegate authority, and then make sure that name resolution works properly with Azure DNS. Real simple to do, real basic. Now we'll take a look at some of the ways that Azure can distribute network traffic. So the whole idea behind this is you have an application running in Azure, and that application is, a multi-level, multi-tier application. Maybe it's a VM scale set with 100 web servers. Maybe it's distributed across 3 different Azure regions. How does Azure manage getting all the traffic that's coming in to those different applications in all those different regions in a manner that ensures that no one region or no one instance or one VM actually assumes all the load? So there's 3 technologies within Azure that help support this. We have something called the Azure Load Balancer, right? This is a basic load balancer that works at level 4 of the OSI stack and will simply balance across a series of endpoints. So if you have a VM scale set, typically in front of that VM scale set is a load balancer that's going to balance everything back and forth. And it can do a couple of different ways, what they call load balancer affinity, where every request can go to a different VM, where it can maintain, if your source IP is this, you'll always go to the same VM because maybe there's session state data. There's different ways that you can configure these things. Traffic Manager, think of this as load balancing for Azure regions. So whereas, within an individual Azure region, I might have a scale set of web servers. If I have 4 scale sets in 4 different regions worldwide, Traffic Manager will look at, if the user is coming from Australia, routing them to the load balancer that services the VM set that's located in Australia. It makes sure that when you do DNS work, for example, DNS round robin, you don't have an Australian user going to a European data center, a North American user going to an Indian data center, for example. It makes sure that you connect to the instance that's regionally close to you. And then an application gateway is a layer 7 web application gateway that works as a reverse proxy, where it terminates the client connection, then reestablishes and forwards onto the internal web server. So it's the highest layer of protection. So if we kind of compare these, how they work. For a load balancer, it's layer 4. For application gateway, it's layer 7. For Traffic Manager, it's a DNS-based technology. The load balancer does any protocols. The application gateway is HTTP, HTTPS, and Traffic Manager is any HTTP or HTTPS endpoint. The endpoints can be VMs or cloud services. For the app gateway, any Azure IP address. And for Traffic Manager, any web app or external endpoint. They all support VNets. For Traffic Manager, it's internet facing only. App gateways and load balancers can be internal. So I can, for example, have a load balancer that's external facing in front of some web servers. And then behind that, I can have a farm of SQL servers with a load balancer in front of that. So I can have an internal load balancer and an external load balancer, or both. And then finally, how does it determine if the endpoint is up? The load balancer in the app gateway will do what's called a probe, and the Traffic Manager will do a web query. And that's how it determines if any one of its given endpoints is in fact available. So load balancer configuration is very straightforward. You do this with the Portal PowerShell or any ARM template, and you're simply adding rules or adding VMs that it's going to sit in front of. So it's a very simple, very straightforward configuration. You'll see us walk through this in the demos. So here's kind of what it looks like. You have a front-end IP configuration. You have a back-end address pool. The back-end address pool represents all the interfaces that are load balanced. So if I have a series of web servers, all the IP addresses that make up those different web servers represents my back-end address pool. We then have load balancing rules that determine how it actually conducts the load balancing. Is it literally going every single request 1, 2, 3, 1, 2, 3, 1, 2, 3, Or is it using something more intelligent, like the source IP address always goes back to the same host so that we have some better session affinity or things of that nature? It has what are called probes. And a probe is how it determines if a VM instance is up. So if I have a series of web servers, it will probe those web servers. If one of those probes fails, it'll consider that web server down and remove it from load balancing. And then finally, it can do port translation. I can, for example, listen on port 80, but internally go to port 8088. So if that's something that you need to implement or choose to implement. So what they often call reverse proxy, reverse NAT. So those are all supported within the configuration of the load balancer. For Traffic Manager, this is a very straightforward implementation as well. You enable Traffic Manager, and then within Traffic Manager, configure the rules that determine which web applications are actually being published. And again, the big thing you gain with Traffic Manager is it will ensure that when you're connecting to an endpoint, you're connecting to the one that's in the closest region to you. So it's a type of geo-awareness for connecting to Azure endpoints. The configuration is fairly straightforward. So you have a load balancer. This example right here kind of shows what it might look like. So I have in each region, East and Central, I have a load balancer that has a couple of endpoints behind it. And then I install Traffic Manager to manage traffic to the load balancers. So anyone that's on the East Coast always goes to the East US load balancer. Anyone on the West Coast always goes to the Central US load balancer. And then finally, we have a web application gateway. So this is a layer 7 application gateway that's failover and performance routing for HTTP traffic. So it can be SSL or straight HTTP. It's based on cookie-based session affinity, so it does require cookies to work properly. And then you can create this with the resource manager, the portal, or with an ARM template. The implementation requirements, you have a backend server pool, which again is similar to a load balancer. These are all the web servers that are behind the application gateway. You have which port and protocols are being published. You have the front end port, and then you have a listener. The listener is what's actually listening for inbound traffic. Now, for those of you that are, been doing this for a little while, or maybe played with the old Microsoft ISA server product, this is very similar to the type of thing that was in ISA server, where you can create a listener. It will assign it a certificate. It'll list on HTTPS, receive the inbound web request, turn around, and then give that inbound web request to other web servers. One of the common uses for this is, for example, if all my web servers are configured for HTTP, I don't want to put certificates on all of them, but I want SSL from the user to Azure. I can set up a web application gateway with a certificate listing on SSL. The request is received, transferred to HTTP, relayed to the web servers, and then as the replies come back, the web application gateway reverses that process, and the reply is sent using SSL. That's one example of where a web application gateway can actually be used. So that's our look at how we configure network traffic distribution within Microsoft Azure.